Hello, and welcome to this deep dive into one of the most fascinating planetary defense stories in human history. It is late 2025, and if you look up at the sky today, you are looking at a crime scene, a laboratory, and a success story all rolled into one. We are talking about the stratospheric ozone layer. In the grand theater of Earth history, humanity usually plays the antagonist. We burn, we pollute, we extract. But there is one chapter where we flipped the script. It is a tale of invisible poisons, scientific detective work, and a moment when every nation on Earth agreed to save the sky. As we stand here in November 2025, the news is complex. The Antarctic ozone hole, that recurring seasonal scar in our atmosphere, has been behaving erratically over the last 3 years, whipped into strange shapes by the aftershocks of a massive volcanic eruption. Yet, beneath these short-term tantrums, the long-term data is undeniable. The patient is healing. Today we are going to bypass the surface-level news and get into the heavy science of how we nearly destroyed our planetary shield and the unprecedented chemistry and diplomacy that is bringing it back. To understand the stakes, we have to look at the architecture of our atmosphere. If you drove a car straight upwards, within 10 minutes you would pass through the troposphere, the chaotic, weather-beaten layer where we live and breathe. Above that, from about 10 to 50 kilometers up, lies the stratosphere. It is calm, it is dry, and it is layered. Sitting right in the middle of it is the ozone layer. Ozone is a paradox. At ground level, it is a pollutant, a component of smog that burns our lungs. But up there, it is a superhero. An ozone molecule is simply 3 oxygen atoms bound together. This specific chemical structure has a unique quantum ability to absorb ultraviolet B radiation from the sun. Without this filtration system, UVB would scour the surface of the Earth, shredding the DNA of plants, animals, and humans alike. Life as we know it simply could not exist on land without this layer. Scientists measure ozone in Dobson units. A healthy layer over Antarctica should be about 300 to 400 Dobson units. To visualize this, if you took all the ozone in the stratosphere and compressed it down to sea level pressure, it would be only 3 millimeters thick. That is roughly the height of 2 pennies stacked together. That is all that stands between us and a radiated wasteland. The story of how we almost lost those 2 pennies begins with an American engineer named Thomas Midgley Jr. in the 1920s. He invented a class of chemicals called chlorofluorocarbons, or CFCs. At the time, CFCs seemed like a miracle. They were non-toxic, non-flammable, and incredibly stable. They became the industrial blood of the 20th century, used in refrigerators, air conditioners, spray cans, and foam insulation. We pumped millions of tons of them into the air. But their stability was a trap. Because CFCs do not react with anything in the lower atmosphere, they do not wash out with rain. They drift upward, taking decades to reach the stratosphere. Once there, they are finally bombarded by the high-energy UV radiation they floated past. The UV light shears off a chlorine atom from the CFC molecule, and the massacre begins. The chemistry here is terrifyingly efficient. It is called a catalytic cycle. A free chlorine atom encounters an ozone molecule, steals an oxygen atom from it to create chlorine monoxide, and leaves behind ordinary oxygen. The chlorine monoxide then collides with a free oxygen atom, drops its passenger, and the chlorine is free again to find another victim. One single chlorine atom can destroy over 100,000 ozone molecules before it is finally neutralized. It is a serial killer that never sleeps. In 1974, scientists Mario Molina and Sherwood Rowland hypothesized that this was happening, but industry giants ridiculed them. It wasn't until the early 1980s that Joe Farman and his team from the British Antarctic Survey noticed something impossible at their Halley Bay research station. During the Antarctic spring, ozone levels were dropping by 50%. They had discovered the Antarctic ozone hole. But why Antarctica? Why did the hole open over the pristine South Pole and not over the factories of Europe or the USA? The answer lies in the polar vortex. During the long, dark Antarctic winter, a strong wind encircles the continent, isolating the air inside. Temperatures drop to -78 degrees Celsius. In this extreme cold, unique clouds form called polar stratospheric clouds. These clouds act as a surface for chemical reactions, activating the chlorine from CFCs and storing it up like ammunition. When the sun rises in September, that light strikes the stockpiled chlorine, triggering a sudden, massive explosion of ozone destruction. The world reacted with the Montreal Protocol in 1987, mandating a phase-out of CFCs. It was the first treaty in UN history to achieve universal ratification. And it worked. But not overnight. CFCs live for up to 100 years, so the damage was baked in. The hole peaked in size in 2006. But fast forward to our current time, the mid-2020s, and the narrative gets complicated. By the early 2020s, the hole was shrinking. But then, nature threw a curveball. On January 15, 2022, the Hunga Tonga Hunga Ha'apai underwater volcano erupted. Unlike normal volcanoes, this one blasted 150 million tons of water vapor straight into the stratosphere, increasing the layer's total water content by 10%. Water vapor is a greenhouse gas, but in the stratosphere, it radiates heat out into space, causing cooling. As we just learned, colder temperatures mean more polar stratospheric clouds, which means more ozone destruction. This is why 2023 saw a massive ozone hole, and why this year, 2025, the hole behaved erratically again, persisting into November. Scientists confirm these are temporary scars from the volcano, not a failure of the treaty. The water vapor will dissipate by around 2028. To truly appreciate where we are, we have to look at the timeline we rejected. NASA led a simulation called The World Avoided. In that alternate 2025, the Antarctic hole is permanent. A second hole has opened over the Arctic. By 2065, global ozone collapses. UV index values in cities like London or Washington, D.C. would hit 15 on a standard summer day. In the tropics, they would hit 3.3. For context, a UV index of 11 is currently considered extreme. The simulation estimates that the Montreal Protocol is preventing 443 million cases of skin cancer in the US alone. We didn't just fix a hole. We prevented a biological apocalypse. Looking forward, if current policies hold, the ozone layer will recover to 1980 values by 2040 for most of the world, and by 2066 over the Antarctic. However, the future holds a strange twist called super recovery. Climate change is warming the lower atmosphere where we live, but it traps heat there, causing the stratosphere to cool down. Paradoxically, a cooler stratosphere outside of the polar vortex actually slows down the chemical reactions that destroy ozone naturally. Models predict that by 2100, the global ozone layer might be thicker than it was in 1980. While this sounds good, too much ozone could reduce UV radiation so much that vitamin D deficiency becomes a major health issue in northern latitudes. But we cannot declare mission accomplished just yet. As the old threats fade, new ones rise. In 2025, the space economy is booming. Rockets, particularly those burning kerosene, leave behind trails of black carbon and alumina particles directly in the stratosphere. A 2024 study warned that a tenfold increase in launch rates could undo our progress. The black carbon warms the stratosphere locally, changing wind patterns, while alumina particles can act like mini-clouds, activating chlorine just like those polar clouds do. Furthermore, desperation to stop global warming has led to discussions about stratospheric aerosol injection, essentially pumping sulfates into the sky to reflect sunlight. While this could cool the planet, it would provide a massive surface area for chlorine activation, potentially delaying ozone recovery by decades. The recovery of the stratospheric ozone layer is the greatest environmental success story in human history. It proves that science can identify a planetary threat, that governments can listen, and that humanity can pivot away from destruction. As we watch the erratic ozone holes of the mid-2020s stabilize and shrink in the coming decade, we are witnessing the Earth healing itself. With a little help from us, the ozone layer is healing. The question now is, can we apply the same resolve to the climate crisis unfolding below it?